Beginning the search for the very best that Britain has to offer its food and drink in half an hour after BBC Two travels a little further afield.
Hello and welcome to a slightly different Local Heroes. This week I'm seeking out some of the pioneers who began modern science, which flowered in the 16th and 17th centuries. This is Europort at Rotterdam, and I've come here because this week all my heroes come from the Netherlands. I'm amazed that the man I want to tell you about now isn't known outside the Netherlands. He seems to have beaten Galileo to the conclusion that little things fall just as fast as big ones. He built an amazing wind-powered vehicle. He was the first person in the world to explain water pressure. He introduced decimal fractions and wrote a treatise on windmills. His name was Simon Stevin. His early life is a bit hazy, but Simon Stevin certainly worked as a clerk at the tax office in Bruges before moving to Leiden, where at the advanced age of about 33 he went to university. One of the things you realise about the Netherlands is that lots of the important cities are really close to each other, so it's quite reasonable for Stevin to pop up in several places. This is the Ouderkerk in Delft, whose leaning tower was the location for an amazing experiment. Science was pretty dull until the end of the 16th century, but then along came the Renaissance, which brought modern art and modern science, and it was led by people in northern Italy and here in the Netherlands. Now there's one experiment that everybody knows about, Galileo dropping heavy weights off the Leaning Tower of Pisa. But what I didn't know, and I was amazed to hear, was that Simon Stevin actually did that experiment first, something like 4 years earlier. He took light lead balls, small ones, and big lead balls, and he dropped them at the same time off this very tower, and it's 45 metres to the ground below, and I do not dare look over. Now, they've just been restoring the roof below, and so I'm not going to drop lead balls, but I am going to drop a 100-gram container of feathers and 600 grams of dried peas in an identical container, and I'll drop them at exactly the same time and see what happens. The ancients said that the heavy one would hit the ground first. It must do, it must fall faster. But Stevin decided to put it to the test. Okay, this is it. Clear below. 1, 2, 3, drop. Stevin listened to the sound as the balls hit the pavement below, and he said they were so close together that the two sounds merged into one. In other words, the heavy ball and the light ball hit the ground at exactly the same moment. This must have been a really amazing moment in Simon Stevin's career. Until then, it was absolutely obvious that the heavier thing would fall faster. In fact, it was so obvious that nobody had even bothered to try it out, and he showed that that was completely wrong. It was a victory, not only for the new scientific thinking, but for scientific experiment and for Simon Stevin. Stevin became science and bookkeeping tutor to Prince Maurice of Nassau, and in fact a lot of Stevin's writings are just Maurice's textbooks. His most famous invention in 1600 was the wind-powered carriage, and in fact Prince Maurice had 2 of them, and they used to sail up and down the beach here at 25 miles an hour. Well, so people say. Okay, 1, 2, 3, go! 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 Maybe the sand's a bit softer than it was in 1600, or the wind a bit less strong. I'll see if it'll go without me on it. Yeah, look at that! Terrific! Now Stevin had a really massive one that would carry 25 or 30 people. And on one occasion, he had 28 of the local dignitaries sailing along the beach, and he turned and headed absolutely straight for the sea. They all thought they were going to die, and at the very last moment he steered away, and they were all saved and much relieved. Simon Stevin was rather embarrassed that he became famous not for his scientific ideas, but for this rather trivial invention of the sand yacht. But what amazes me is that outside the Netherlands, we've never even heard of this. And yet he was clearly one of the great original thinkers who gave a kick-start to modern science. I'm very fond of heroes who use curious pieces of apparatus. A man who lived right here in Leiden used church towers and triangles to measure the circumference of the earth. His name was Willebrord Snell van Rooyen, or Snellius to his friends. Willebrord followed in his dad's footsteps and became a lecturer on maths and astronomy. But he was quite a traveller too, and made friends with the great astronomers of his day like Tycho Brahe and Johannes Kepler. On his travels, Snell found a problem to solve, to repeat and improve upon the feat of Eratosthenes in Egypt 2,000 years before. Now, Willebrord Snell's ambition was to measure the circumference of the Earth, and this is the place he chose to do it from. Isn't it fantastic? He deliberately chose a dead flat field. It's actually reclaimed land. It used to be complete swamp, and all the water has been pumped out by windmills. And in his day, it was probably quite a lot swampier than this. And he chose it because it was between the town hall tower there in Leiden, which is unfortunately behind those trees now, which have grown up, and the town hall tower down there in Zoeterwoude, again behind the trees. And he picked himself a line along this field. Now, the only tape measure he had was this, a piece of chain, and you'll probably recognise at once that this is one Rhineland rood, which is actually 3.67 metres. And what he did was to stick a post in the ground, probably actually in this very hole where I am, and he put his chain over it like this and ran it down to the ground, and then he set off south 3.67 metres like that, and then he stuck another post holding that end down like that, and then he went and picked it up off the first stake, and he did the same thing all over again. And he did this not just twice, he did it 87 times, very carefully stretching the chain out, and that gave him a precise baseline of 327 metres. And to make absolutely sure, he came back again in the middle of the winter when the whole place was frozen solid, and he did it again on the ice. And then he had a beautifully measured baseline, and from that single measurement of 327 metres, he was able to calculate the circumference of the whole Earth. Like many Dutch scientists, Snellius used towers in his work, and this one on the town hall at Leiden was the starting point for the next part of his mission, to measure the rest of the country using triangles. He wanted to find somewhere where he'd get a really good view of the countryside. And I expect he came up here because you ought to be able to see some way from here. Wow, look at that. Now, coming up here, he just had to use a very simple instrument, more or less like this. It's just a pair of pointers on the end of two angles, two pieces of wood. And all he had to do was to measure the angles between churches. So there's a church there, and I look along and line up that pointer with the church spire, and line up that one with that church spire, and then I take the thing down and I measure the angle between them. From each end of his baseline, Snell measured the angle to this tower, making his first triangle. By simple geometry, once he had the length of one side, he could calculate the length of the others without actually measuring them. He then used the new lines to build up more triangles, calculating the distances between towers without measuring them on the ground. Once he'd measured his baseline and all those angles between the landmarks, he was ready to triangulate, and in fact wound up with this, an accurate scale map of eventually the whole of Holland. Let me explain. This yellow bit here is his baseline, those 87 Rhineland roods in the polder. And here, this rolled up 10 guilder note is meant to be one of the church towers to which he measured the angles. You see, he measured this angle here to the church tower and this angle here, and knowing that length, he was able to calculate this distance. But then, of course, he measured the angles to the church towers here and here and here and here, and all over Holland. And here is his accurate scale map, which ran all the way up north to Alkmaar and all the way down south to Bergen op Zoom, and then he knew the precise length of Holland. From the stars, navigators knew how many degrees north and south those borders were, but not how far apart. Snell worked out the length of 1 degree on the surface of the Earth and multiplied by 360 to get the circumference of the globe. Snell was rather unlucky. 15 of his children died during his lifetime, and his house was destroyed when a ship full of gunpowder blew up. He finally died in 1626, and his memorials are triangulation points on top of hills all over the world. At a time when Dutch explorers were sailing the 7 seas and settling in the New World, one man stayed here in Delft and discovered his own new world in a drop of water. He was born right here by the east gate in the city wall, and his name was Anthony van Leeuwenhoek. Leeuwenhoek's father was a basket maker, and when Anthony was 16, he became apprenticed to a Scottish textile merchant, eventually settling in Delft. He almost certainly sold cloth in this very market, and he probably used a magnifying glass first to inspect the quality of his cloth, to count the number of threads in every inch. But apparently he didn't think of using a microscope until 1668, when he was 36 years old. He was inspired by a copy of Robert Hooke's Micrographia that he saw when he was visiting friends in London, and was particularly impressed with Hooke's detailed drawings of taffeta and linen. Hooke's Micrographia contained a description of a simple microscope that was little more than an extremely powerful magnifying glass, using only a single lens. In about 1671, Leeuwenhoek set about making his own microscopes and lenses. The microscopes that van Leeuwenhoek used were actually just tiny blobs of glass. Now, if you take a blob of glass like this, well, this has got water in it, but it's like a blob of glass, if you put it in the right place, you get tremendous magnification. And he realised that if he wanted very big magnification, what he needed was very, very small blobs of glass. The magnification of a lens is greater if its surface is more curved. The surface of big spheres is gently curved, but the surface of tiny spheres is tightly curved, so they make the more powerful lenses. This was how he made them. He took a blow lamp, and he took a very, very thin piece of glass. And then what he needs to do is to heat the very, very tip of it to make a tiny little blob on the end of his thin piece of glass. And that is basically a van Leeuwenhoek microscope. Now let me show you how he actually used it. Because it's so tiny, it was very difficult to hold in front of his eyes, so he took 2 sheets of brass and clamped it between them with a hole drilled through each so he could see through, rather like this. Here is a blob of glass, and it's clamped between this sheet of wood and this sheet of wood. And here is the specimen of pond water that I want to look at, and I've got a mechanism here for moving this in and out and up and down. And if I look through there, what I can see is actually a whole lot of greeny blue blobs. I think you'll be able to see them too, and they're actually algae. They're called volvox, living things in pond water. Now remember, to get huge magnification you need a very, very, very small lens, and I've made one here. This is more or less like his. Do you see the lens is that tiny, tiny thing in the middle? It's actually a sphere of glass about 2 millimeters across, and it's sandwiched between 2 sheets of brass. You can just about see there's a piece of brass folded over to hold the lens between this side and this side. And I'm going to look at a little specimen of pond water here, which I need to put in this slot behind the lens. And then if I hold it up to the light, I can see there. It is quite amazing. What I can see is a lot of filaments, greeny blue filaments, which are actually filamentous algae. You can see inside the filaments, you can see spirals, and the thing is actually called Spirogyra. These were the first microorganisms ever seen, and Leeuwenhoek was the first to see them. I've tried a couple of other things he looked at. This is a bee through my microscope, and a human louse. But I won't be repeating one experiment. He nearly blinded himself by watching gunpowder explode. He sent hundreds of letters to the Royal Society in London, covering 50 years of observations, which caused so much controversy he had to call on priests and medical men to validate his claims. He was very secretive about his methods, but went on to discover sperm, which he obtained without defiling himself, and was the first to see blood cells. Leeuwenhoek must have got magnifications of up to 500 times.
Haringkie blanke, alle 5 voor 1 tientje, man.
He was very interested in pepper, and he wondered if pepper tasted hot because it had little spikes on it. So he took some peppercorns and he ground them up and left them in water in his office for a few days to sort of mature. Thank you very much, yes. And then he looked at them and he saw some very tiny things moving about, and these were bacteria. It was the first time anyone in the world had seen bacteria, and his technique was so good, thank you very much, that nobody else saw bacteria for another 200 years. Of all his amazing observations, the thing he was most proud of was watching the circulation of the blood in live eels. Now here is an eel. This is no longer live, but he took an eel that was alive and he arranged a special holder on his microscope so he could actually watch the blood going around inside the eel. Fantastic observation. Unfortunately, his work got the better of him because he was looking at a disease of the diaphragm of sheep, and he got ill and died, and it's now called van Leeuwenhoek's disease. Anyway, he was 90 years old, and I'd like to eat to the tribute of my hero, van Leeuwenhoek, who saw the most amazing things through his microscope. That's really good. Oh, like this. Right, thank you. Right. It's a warmish day here in Amsterdam, but just how warm is warmish? Until my next hero came along, I couldn't have told you that, but he made it possible for people to talk about temperature. He lived just down the road here, and his name was Daniel Fahrenheit. There's no portrait of Fahrenheit, but he was born in Danzig in Germany, now Gdansk in Poland, and he became a scientific instrument maker, settling in Amsterdam. Fahrenheit didn't invent the thermometer. They'd been around for 100 years or so. Galileo used spirit thermometers like this. Spirit in the bottom, air above, and the tube goes all the way down to the bottom. And the idea is that when the air warms up in the top here, it expands and pushes the spirit up the tube. Let me show you with this glass of warm water. I put it in there, and you'll see the spirit come rushing up to show that the water is warm. So it certainly shows whether things are warm or not. But unfortunately, the spirit tends to evaporate, and also it's because it's exposed to the atmosphere, it varies greatly with atmospheric pressure. Fahrenheit realised that mercury would be a whole lot more convenient. For one thing, it isn't volatile like spirit. For another thing, you can see it easily through the glass. And for a third thing, it actually expands much more evenly with temperature. So what he did was to put his mercury in a bulb like that, and then at the other end, he sealed the thermometer so it wasn't exposed to the atmosphere, and that meant that the behaviour wasn't affected by atmospheric pressure. At his house on Keizersgracht, Fahrenheit lectured on the history and use of the thermometer. It's now a smart lawyer's office. Once he'd invented the mercury thermometer, Fahrenheit realised it was important to set up a universal scale of temperature. The thing is, there were lots of scales about, but everyone had their own, and that meant that if I did an experiment at, say, 30 degrees, you wouldn't know what that meant unless your scale was the same as mine, and it wouldn't be unless I lent you my thermometer, which obviously I wouldn't want to do. So Fahrenheit went off to see a chap called Klaus Römer, who'd done some work on this. And Römer had 2 fixed points to make up his scale. First, melting ice, and he said that ice melted at 7.5 degrees, 7.5 degrees Römer. And the other fixed point was boiling water, and he said that water boiled at 60 degrees Römer. And that was Römer's scale. Now, 7.5 seems a slightly peculiar number to choose, but he did that because he knew that the lowest temperature in the universe could be achieved by mixing ice and salt, and then you would get a temperature of 0 on his scale, at 0 Römer. So now we have these 3 points on the Römer scale. These are the 2 fixed ones. Fahrenheit thought that was a pretty good idea, really, but he thought this was too narrow a range. He wanted more degrees in there so that he could measure things more precisely. And what's more, he wanted an intermediate fixed point. And he chose the human armpit. He said that the armpit of a healthy male, like me that is, should be 90 degrees. So here we have the armpit temperature, 90 degrees Fahrenheit. Then he multiplied everything by 4 so that 0 remained 0 and melting ice was 30. And he announced that the temperature of boiling water was 212. And there we have, in all its glory, the Fahrenheit scale of temperature. But not quite. He figured that changing 30 degrees to 32 and 90 to 96 would avoid awkward fractions. And then it was found that armpit was actually 98.4. And that was the Fahrenheit scale that lasted for 250 years. Really remarkable, particularly as it was Römer's idea in the first place. But Römer didn't write it down. Fahrenheit wrote this all up and published it, and then it was Arrivederci Römer. A bit later, a Swedish chap called Anders Celsius came along and devised a new and even simpler range of temperature from 0 melting ice to 100 at boiling water. But he didn't live in the Netherlands, so I'm going to drink to Daniel Fahrenheit. Without him, all I could have said was that this beer is nicely chilled, but with his help, I can tell you it's at exactly 41 degrees Fahrenheit. Perfect. Thank you, Danny. This is The Hague, the political capital of the Netherlands, and the birthplace of the man whom the Dutch regard as their greatest scientist of all time. He invented the pendulum clock, and his name was Christian Huygens. Christian Huygens was born 13 years before Isaac Newton. His father and grandfather were high-powered diplomats, and he was sent off to study law in France, where he was a favourite of the Sun King, Louis XIV. In the 1650s, Christian and his brother built a telescope better than any before, and with it he spotted a moon going round Saturn, and became the first person ever to work out that Saturn had rings. Galileo and others had called them arms. This is the very centre of The Hague. I've just come through from Parliament Square, and I reckon that where these buildings are now must have been where Christian Huygens had his childhood home. He became a seriously good astronomer, and he realised that for precise astronomical measurements he needed a really good clock. So in 1656 he invented the pendulum clock, the most accurate clock in the world. To show you how it works, I've turned my own bicycle into a clock. For a clock you need 3 things. First, a power supply, and usually they're used weights, so I've put a bag of lead shot there attached to one of the pedals. Next, you need a counter, like a second hand, and I'm going to use my back wheel, and you have to imagine a second hand painted on it. And if you lift up the weight and let go, it spins the second hand round, but it's not keeping time at the moment, it's just spinning round in an uncontrolled way. So I need a regulator. And for his regulator, he chose a natural timekeeper, the pendulum. And here's my pendulum, suspended up there with a weight at the bottom, and if I pull it, it just swings backwards and forwards naturally with a rhythm of about a second for each swing. His brilliant idea, his stroke of genius, was to couple the 3 things together to make a working clock. And the way you do that here is by swinging in these bits of aluminium, which nowadays are called pallets. And then you'll be amazed to discover that I've actually got clockwork. Just look at this. Lift up the power supply, let go. It doesn't even need a little push, it goes on its own. And you'll see that the spokes have to escape between the pallets in order for the wheel to turn round. And this is actually called an escapement mechanism. The wheel can only go round as fast as the pendulum allows it. So each of these spokes corresponds to one swing of the pendulum. And that means that my second hand is now clicking round in seconds. It's actually even more cunning than that, because if you look carefully, you can see that these pallets are bent up a little bit at the end. So each time one of them is hit by a spoke, it's given a little push, and that pushes the pendulum. Now that we've all got quartz watches, the pendulum clock seems a bit old-fashioned, but in 1656 it was an amazing advance in science and technology.
In the 1670s, the Dutch were at war with the French, so Huygens had to come home. He lived here at Hofwijk, the family's country residence. It's now a museum stuffed with wonderful Huygens clocks and books. He worked out the mathematics of the pendulum and devised a trick to make them run precisely.
And here we are, a genuine Huygens clock. Well, he didn't make it himself, you understand. He was an aristocrat and his dad wouldn't let him do any craft work. So he got his friend, the clockmaker, Peter Wiesbach, to make it for him. And you can see that the pendulum is swinging through quite a wide arc. And up at the top, its swing is controlled by these brass cheeks. Now the point of these is to force the bob to swing in a mathematical curve called a cycloid. Because he'd worked out that if it swung in a cycloid, it would always take exactly the same time for each swing, no matter how far it swung. Isn't it a beautiful thing? Huygens was charming, suave, intelligent and rich, so it's hardly surprising that he had a string of lady friends. But he never actually got married, partly perhaps because he was a bit of a prig. At one point he wrote about the folly of the young people of Amsterdam, which seems to me excessive and unbearable. And when he wrote that, he was all of 21 years old. After he retired here, he unfortunately got rather depressed. Partly, no doubt, because his brother died, but partly, I expect, because he was missing the bright lights of Paris. Huygens was an amazing scientist. He dreamt up an elegant new theory of gravity and suggested that light comes in waves. He disagreed with Newton about that. He found new ways of grinding lenses for microscopes and telescopes and became a brilliant astronomer. However, he did convince himself that the planets were inhabited, and he described in detail the shipbuilding and other things going on Saturn and Jupiter. He was the finest mathematician in the middle of the 17th century, but he'll always be remembered for his pendulum clocks. I'm sorry, that's all the heroes from the Netherlands. See you next time!
If you would like to try some experiments from the programme, to visit some heroic sites, or just find out more about my heroes, details are on the local heroes website at www.bbc.co.uk/education.